10Cs, we continue the algebraic process of solving systems of equations. Last lesson, we looked at the substitution process, where we substituted an expression from one of our equations into the other equation. Today, we're going to look at the elimination method. Now, here's the trick. Substitution, we substituted something in. Little hint, with the elimination, we are looking to eliminate things. Yes, hence the name elimination method. So, two processes algebraically. When it comes to solve algebraically, honestly, I don't think on any assessments we ever say you must use a process. Algebraically says you can't just punch it into a calculator and come up with an answer. It means you have to show the algebra. If you like the substitution method, you can use it. If you like the elimination method, you can use it. But what's really important to understand is that each of them has their pros and cons for different situations. You need to be familiar with both. But on an assessment, you can use whichever process works for you, even though usually one method will tend to be a little more advantageous. So be familiar with both. So let's jump into it. Elimination method of solving a system of equations. Here we go, page 18 of the notes. Two equations, make it a system, and two different variables, an x and a y, make it a system of equations. So, a couple things. The first thing we want to make sure of are things lined up. That's kind of important with the elimination method. I want to make sure that my x terms are lined up together. I want to make sure that my y terms are lined up together. I want to make sure that my constants are lined up together. Technically, they can be lined up in any order, but you want to make sure that x's are lined up with x's, y's with y's. It just simplifies this process. I've had students in the past that say, oh, I don't need to do that little shuffle at the start. You have lots more chance for boneheads to happen. All right, so what it is with the elimination method is we want to try to eliminate a term. In this first system, it's really easy to eliminate a term. If I take a look at the two equations and I want to combine them together, well, if I just look at adding these two terms together, what's nice is if I have 2x plus 5x, well, that's going to give us 7x. If I look at my constants, 10 plus 11, that's 21. Excuse me. But here's where the magic of the elimination method works. When I combine a negative y, or if you prefer a negative 1y, and a positive y or a positive 1y, negative y and a positive y, well, they have a value of 0. They cancel each other out or eliminate the y values. Therefore, if I just combine these two terms, I end up with 7x equal to 21. I've eliminated the y terms, and now I only have x's that I can solve for. Divide both sides by 7, and x works out to be 3. So that's the elimination method, where you want to eliminate one of the terms, the x terms or the y terms. It's not always going to be quite this straightforward, but simply by adding the two equations together here, x's gave us 7, but the y's canceled, and that's what makes it nice. However, we line things up, we combine the two equations, and that should result in eliminating a variable term. In this case, we were able to eliminate the variable y. But please make sure, once it's eliminated, you algebraically solve for the variable that remains, but make sure, don't forget, solve for the second variable. We've solved for x in this case. We still have to, as we did with the substitution process, we still need to solve for y, knowing that x is equal to 3. I can substitute that x into either equation. It doesn't matter. y should work out to be the same in both. So I'm just going to use the first one. Excuse me. 2 times 3, subtract y equals 10 by putting the 3 in for the x. 6 minus y equals 10. Move the y over here to become a positive y. Move the 10 over here. 6 subtract 10 is negative 4. So our solution is 3, negative 4. And as always, like we've been doing all along, the last thing you could do is a verification. I'm not going to verify and show it. We've seen it enough. You can do a verification and make sure that when x goes in for 3, y goes in as negative 4 to both equations are balanced. So there's an easy one for the elimination method. Let's take a look at number 2. So number 2, like the little notes say, arrange the equations so everything's aligned. We have x's aligned, we have the y terms aligned, and we have our constants aligned. Perfect. Now, last question, we simply at that point added the 2 equations together. If I add these 2 equations, 1x and 1x is 2x, 2y and a 1y is 3y, and 10 plus 7 is 17. There's no elimination having occurred here. So the last equation was the last system, the first one we did, was nice because our y's canceled. Here, we see that we can't cancel anything by combining the terms. So here's the most important step in the solving process that we didn't have to do last time. Is you are probably going to have to multiply one of the terms or equations, one of the equations. Sometimes it might be both, but we need to multiply one of the equations by a factor so we can create a set of additive inverse terms between the 2 equations. I need to have my x's as additive inverses to each other, positive, negative, same term. I need to have my y's as added as an inverse to each other, same number but different signs. Now remember, when everything in an equation gets multiplied by a factor, if I multiply everything in this equation by something, the equation stays equivalent. It just gives us different values. So that's where we have to look. What could we multiply an equation by to create an additive inverse? Well, there's 2 possibilities here. We'll look at both. We could multiply that first equation by -1. Now, multiplying by the 1 doesn't do anything, but multiplying by the negative, if everything gets multiplied by a negative here, all of a sudden I end up with a negative 1x. I end up with negative 2y, and I end up with negative 10. So now I have this new system of equations, because I didn't change my first one, or my second equation here, but my first one after doing the multiplying, well, we now see positive x and negative x, there's the additive inverses we needed. So now I can add the 2 equations. X and negative x is 0x. They cancel out. I have 1y and a negative 2y, which leaves me with a negative 1y. And I have 7 and negative 10, which is negative 3. Multiply the first equation by -1, create the additive inverses, cancel out, and now I can divide both sides by -1, and y equals 3. There you go. This multiply one of the equations is usually what you're going to have to do. There will be some questions potentially where both equations will have to multiply, but we didn't have to in this case. Combine the terms in the 2 equations together. We eliminated one of the variables. We solved for the variable, and now we have to solve for x. So go back to the original, get rid of some of my scratch work. Which equation could I substitute into? It really doesn't matter. I'm going to substitute into the second one. We believe that y equals 3. So x plus 3 for the y should equal 7. X is 4. So we're saying the solution for this system is 4, 3. And there you go. Eliminate a set of variables, or a set, the x's or the y variables. Now, very quickly, same question. I want to do it a second time. You don't have to, but pay attention. What else could we have multiplied by? Well, this one was kind of nice because we just wanted to change the sign, but I could get rid of the y terms in this one as well if I multiplied the second equation by -2. So if everything multiplied by -2, I would have -2x minus 2y equals -14. First equation I'm not doing anything to. I'm just going to bring it down and line it up just so I can see the two of them together. But this time, if I multiply the second equation by -2, there's additive inverse. Our y's can cancel out here. -2y, +2y. Those would cancel out, and I would be left with -1x equal to -4. Divide both sides by -1, x equals 4. It's the same x value we had when we solved it by eliminating the x. So you often have multiple possible solutions here. And if x is 4, you can substitute in y will end up being 3. So we get the same solution for 3, but I did it two very distinctly different ways. The first time, eliminating x's. The second time, eliminating y's. So you have choices with this process. Take a look at number 3. So in this case, the first thing, arrange the equation so the terms are lined up. We need to do that. Our a's are nicely lined up, our b's, but I want to take this -12 and move it over to the other side so that everything is lined up nicely. So I would have 4a plus 3b equals +12. Now my a's are lined up, my b's are lined up, and my constants are lined up. So now I need to take 12a plus 10b equals 48 and 4a plus 3b equals 12 and figure out what can I multiply one of those equations by in order to eliminate a or b. Well, this shouldn't really be rocket science. 12a and 4a, well, if this 4 could easily be made into a 12, but I also need the additive inverse, so I'm going to multiply my second equation by -3. Because -3 times 4a is a -12a, and that'll cancel with my 12a. So we would have -12a minus 9b equals -36. Keep that first equation, and I'm just going to rewrite it down here so it's nice and easy to compare the two. So I changed my second equation by multiplying by -3. Now I can combine all these terms. -12a and +12a, there's our elimination of the elimination method. -9b and 10b is a +1b. -36 and 48 is +12. So we get b equal to 12. And at that point, don't forget, always solve for the second variable. Since I can read this one, that's the one I'll use. 12a plus 10b equals 48, and we believe that b is equal to 12. So we have 12a plus 10 times the b value, which is 12, equals 48. 12a plus 120 equals 48. 12a, when I substitute in there, will equal, oh, I got to pull out my calculator. That one hurts the head a little bit. We end up with a -72 because I subtract both sides by 120 equals -72. And when I divide both sides by 12, we get a equal to -6. So our solution A, negative 6, B, 12. There's our solution. We can substitute back in, and substituting back in would verify that negative 612 in those original equations would create balanced equations. Now, just very quickly, in this case, it was easy to get rid of the A's. Would it be easy to eliminate the B's? Could I multiply one of those equations by something to eliminate a B? No, it wouldn't be as easy. It wouldn't be one step. But let's talk real quick about this. What could we do just if I wanted to eliminate B's? What could I multiply by if I wanted to? Well, this is the case where we could multiply both equations. If I multiplied the top equation, everything by 3, I would end up with a 30b. And if I multiplied the second bottom equation by negative 10 and 3b would be negative 30b. So if both equations got multiplied by a value, well, we could cancel out and eliminate the b's. So again, multiply both equations, we could get rid of something that's not as obvious. But I think you'll find the vast majority of questions, like we just did, have a quick, easy way to eliminate one of the variables. Number 4, pause the video, stop it, give this one a try on your own, see what you come up with, and then rejoin and we'll do it together. So first things first, I'm just going to take this top equation and I'm going to rewrite it. Everything's nicely lined up, but I want to move my 11 to the other side so that I'm consistent here. X's are lined up, Y's are lined up, constants are lined up. 5x, 6y, negative 4, 4x, negative 3y, negative 11. Is there a quick, easy multiplication to create additive inverses? Hopefully you saw that this bottom one, if I multiply it by 2, the 2 and the negative 3y will give us a negative 6y, which will cancel with the y. So multiply everything by 2. 8x minus 6y equals negative 22. I need to keep that initial equation here. So that's a 5x plus 6y equals negative 4. So I changed the first one by multiplying by negative 2, but this equation just stays as is. If I combine these, 8 and 5 gives us 13x. Y's eliminates. Negative 6 and a positive 6 eliminate, and it will equal negative 22 and 4 is a negative 26. Divide both sides by 13. X is negative 2 by eliminating the y's. Finish it off. We need to still solve for the the y values because we believe x is negative 2. So I'll substitute into this equation because I can read it. And we have 5 times negative 2 plus 6y should equal negative 4. Negative 10 plus 6y equals negative 4. Add 10 to both sides. 6y equals 6. And y equals 1. Negative 2, 1. There's our solution for that system after eliminating values. Number 5, special one. Give it a try real quick. Pause the video, see what you come up with, and then we'll join together. Here we go. Now this one's kind of an interesting one. I don't have the constants on the other side of the equation, but everything's lined up. So it's not aligned. X's are aligned, Y's are aligned, constants are aligned. Not the same way we have, but I can leave it like this. In this case, again, we have choices. We could eliminate all kinds of things, but I see the first thing that jumps out at me are these X's. I have a negative 4x and a positive 2. So if this were multiplied by 2, and I rewrite it down here, 2 times 2x Well, that's now going to give me 4x. It's going to give me negative 10y. And it's going to give me negative 22 equal to 0. So there's the two equations now that I want to combine. Negative 4x, positive 4x, eliminates. Perfect. Positive 10y, negative 10y, eliminates. Not so perfect. Negative 3 and negative 22, negative 25 equals 0. All of our variables disappeared. What does that tell us? Well, the math is correct that we did, but this isn't true. So like last lesson, sometimes if the math gets to a point where it's just not true, that tells us there's no solutions. There you go. There's no solutions in this case. Here's why. Again, go back a couple of lessons. If I isolated my y here and I put it into the slope-intercept form, I would be left with 2/5 x minus 11/5 is y. And if I isolated y here, I would be left with, by isolating that y, 2/5 x plus 3/10. There's my slope-intercept. Slope-intercept, slope-intercept. Slopes are the same. And when two lines have the same slope, they're parallel. Well, not the most parallel lines, but parallel lines have no solutions. So the math just got to a point where it didn't work. Why is that? Because if I look at this graphically, I see they're parallel lines and there's no solution. There you go. Solving through elimination. Now, a couple add-on questions. These are important that you understand. Solve the system of equations here. Everybody loves fractions. What does this tell us? Well, fractions, ugly, ugly. But because we don't have to work with x, like single x's or single y's and isolate, we can go back to that process of eliminating fractions, eliminating denominators. We did this earlier in the course. So I want to, before I even start the solving, I have a 6, a 4, and a 4. What's a common denominator that everything could be multiplied here? Common denominator could be 12. If you recall, that means we would have 5, 6x times 12 over 1. Subtract 3/4 y times 12 over 1. And that would equal negative 17/4 times 12 over 1. And this would allow us 6 and 12 will cancel by 6, a 1 and a 2. We're left with 10x. Negative 3/4 y times 12. 4 and 12 will cancel by 4. Leaves us with subtract 9y. And negative 17/4 times 12 over 1. 4 and 12 becomes a 1 and a 3. Negative 51. So there's the equation we could use instead of this first equation. Now, I haven't even started the solving eliminating process. I've started with the get rid of denominator process. So there's the new equation that'll be easier to work with. X over 3 plus y over 4 equals negative 9/4. 3s and 4s. What's a common denominator there? Again, 12 actually works nice. So if every part of that one gets multiplied, x, and instead of x over 3, remember we could think of that as 1/3 x times 12 over 1 plus 1/4 y times 12 over 1 equals negative 9/4 times 12 over 1. Every term multiplies by the 12. Now I can cancel 3 and 12 by 3, leaves me with a 4x. Here, 4 and 12 by 4 leaves me with 3y. And negative 9/4 and 12, 4 and 12 by 4 leaves me with negative 27. And so this second equation, if I multiply everything by 12, here's my new equation without fractions. And now I have a system of equations that would be nice to work with. So I'll just eliminate this work because I don't need it anymore. I've done that. And now I have a new system that's equivalent to the original system, but it's now easier to work with in this process. So let's finish it. 10x minus 9y equals negative 51. 4x plus 3y equals negative 27. Negative 9y, positive 3y. Multiply everything in the bottom equation by 3. That'll give us a positive 9y and will allow us to cancel the y terms. So the first equation stays the same, and the second equation we're multiplying by 3. And there we go. From there, now I can combine these. 22x, y's eliminate, leaves us with a negative 132, I believe. A negative 132, and then I can divide the 132 by 22 and get a value of 6. So x equals negative 6. Now I want to solve for y. If x equals negative 6, substitute into one of our equations. I'll substitute into the second one. 4 times negative 6 plus 3y equals negative 27. Negative 24 plus 3y equals negative 27. Add 24. 3y equals negative 3. Divide by 3. And y is negative 1. So negative 6, negative 1, there's your solution for that system. But first, it's like it's 2 questions in one. Eliminate denominators to get the new system, and then we solve the system. Lots of work there. It's possible, but it's just a lot of work. Your assignments, textbook, page 437, booklet, page 21. If you want more practice, there are questions as well, booklet, page 20, that have solutions. Only way to get good at the elimination process is practice. Give it a try, practice it, and we'll see you next lesson. Enjoy.